Hi, welcome to day 5 of the lecture 5 of the Introduction to Proof videos I'm doing for a general introduction to the art of mathematics. Today we're going to be going over section 1.5, which is about algorithms. I think technically that's a computer science topic, but there's certainly some math in it, and a lot of math can be viewed as algorithmic. So it's reasonable for a student of math to know a little something about algorithms. So today's talk will be in, 5 parts? A little introductory stuff, intro to algorithms. The particular algorithms we're going to look at are the one in bullet 3 there, the division algorithm, and then the Euclidean algorithm in the very end. So this is a picture taken from the History of Math archive at MacTutor at St. Andrews University. It's a stamp from the former Soviet Union. That's you can tell that by up in the upper right corner. CCCP is the initialism for what was USSR in English. I've been taking a Duolingo course on Russian, so I can tell you a little bit about their alphabet. They use the Greek pi for the letter P, and so this funky-looking thing that looks almost like a Y is pronounced ch, and so that's pochta. It's basically post or post office. The person pictured on this Russian stamp, you may be asking, why is he doing that, is well, this would be pronounced Muhammad. I don't know if I know that was his first name, but his last name is famous. It's Al-Khwarizmi, and that is the second letter of A something here is the Cyrillic version of L, which is related more to the Greek lambda than it is to our L. And the little B after it is actually it's called a soft sign. It has no pronunciation. So that's Al, and X in Russian and several other languages is pronounced sort of with a like a K, but really far in the back of the throat, like that. Al-Khwarizmi is how you would say that, I guess, in Russian, but Al-Khwarizmi in Arabic. So this is how it's usually transliterated into English, Al-Khwarizmi. He was famous during the period of time when, after the Roman Empire fell and nothing had really happened in Europe for quite a long time, sort of the era known as the Dark Ages. I think this was about 800 AD. Al-Khwarizmi was the most famous mathematician at the House of Wisdom in Baghdad. And this House of Wisdom was pretty important because it preserved a lot of ancient Greek knowledge and knowledge from India, things that had been lost to the West. So, yeah, that was kind of a big deal. A little bit like the Library at Alexandria before it served a function to contain all the world's knowledge. He's famous for the term algebra, which eventually morphed into the word we named the subject of algebra. Right? He wrote a famous text on it, and that text got translated into Latin, and somehow his name came out like this, Algorithmi, instead of Al-Khwarizmi. So yeah, that's the way languages work, I guess. Eventually, a little bit more morphing happened, and the algorithmy turned into algorithm. That's what we're going to be looking at today. Now, what is an algorithm? Well, put simply, it is a very precisely defined procedure for accomplishing some task. The level of precision depends on the audience, right? So most of the time, algorithms are intended for computers to run, to calculate something. And in that case, the precision has to be extreme. You have to tell the CPU and the computer precisely what to do at every single step. Humans don't tend to do well with that kind of level of precision. So we we use other means of specifying algorithms, in particular, well, we're going to talk about a couple of them. Why do I have the first line of a joke here? So it's an object lesson, and it's also kind of a funny joke, I suppose. So there's a programmer. His wife sends him to the grocery store to pick up a few things. She wants oil, flour, uh, sugar, and she says, "Get some bread. Get a loaf of bread." And then she goes, "Oh, and if they have eggs, get 6." So he comes back from the store with the oil and the other stuff and 6 loaves of bread. And she's like, "What are you doing? Why do you have 6 loaves of bread?" And he goes, "They had eggs." So, yeah. So she sends him back to the store. There's a continuation of the joke. She sends him back to the store and says, "Get 6 eggs, and while you're there, get some milk." He never returns. If you don't get that, it's okay. I'm gonna beat it to death. We'll talk about it. Some of the elements that we'll see in algorithms are assignments. That's one of the biggies. It allows now technically assignments would usually be including other algorithms within your work to set a variable equal to the result of some function means that function had to be defined by an algorithm. But your basic mathematical manipulations go into assignments. You can set variables equal to something. That's an essential element. Conditional execution, tests and conditional execution. That means, remember when she said, if they have eggs, get 6? Well, obviously she meant get 6 eggs, but that was conditional. If they have something, do one thing. And if they didn't, I presumably do another thing. Um, so, yeah, we'll see some examples of that. Looping structures. This is what happened when the guy never returned in the second one. She said, while you're there, get milk. And the entire time he was there, he was getting more and more milk, I suppose. Uh, yeah. So whiles are a type of loop. They're dangerous because if the condition that you set for doing the thing, doing the repeated operation, never turns false, you're kind of screwed. That means you sit there doing it forever. This is the joke of the programmer is he's away forever getting milk. There are some looping structures that are designed in programming languages to be sort of better in that regard. They don't tend to get stuck in infinite loops. But infinite loops is one of the pitfalls of programming computers. It's sort of the classic way to mess up. So we'll generally watch for it. But I'm going to actually show us a particularly bad form of pseudocode in which it has a type of statement called a goto. Gotos are notorious for causing people to get into infinite loops. Finally, you've got to have some way to say, "Oh, we're done," and return the answer. Right? So these 4 elements are enough to do a tremendous amount of things in computing. Okay, so I said we'll generally have very precise programming language or even assembly language descriptions for a computer, but for human beings, that level of precision isn't what we want. We want a sort of a more broad level look at things. So one way to do that is something called pseudocode. Another way is flowcharts. I'm actually wearing a flowchart today. I don't know if you guys can see this in the. It's a T-shirt from this comic strip called XKCD, which is. I've got links here to a couple of their comics. I think it'll be. I'll put the links in the description of the video so you can click on these and see them. I'm not wanting to get into trouble with Randall Munroe because, frankly, I'm a fanboy of his. He's really a funny webcomic author. So I'm not going to be going through these on this on this video, but I do recommend them to you. And once you see a few of his comics, you'll probably get hooked and want to look at it every day. Okay, so program flow. One of the things when you do have a pseudocode or a flowchart, representation of an algorithm, you want to think about sort of you can think of it with your finger. I often do that. You trace through the thing with your finger. But the idea is that at any instant in time, your program sort of exists at some point in that algorithm. It's moving through the algorithm, except for before it starts and, of course, after it ends. I often like to imagine a little bug or something traveling along through the flowchart, and it does it moves in the correct direction based on the the computations it makes while it's going. Tracing a program literally means doing that. You think about where that bug, where that flow is at any point, and you usually keep track of what's happening with any variables so that that's a good way to double check on things that you haven't made a mistake. So that leads to something called a trace table. Um, Trace tables most often are used when there's one single big loop. Sort of if a computer program involves a lot of different loops in different places, there'll still often be an outside loop, the main loop, they call it. So each time you go through the main loop, tell me the values of all the variables and write them in a table. That's what a trace table is. We'll see that in an example of that in a sec. All right, well, with that very brief intro, let's look at an example so that we can actually sort of see these features. The division algorithm. Now, this is a really simple algorithm, and it's not the final version of it that anybody would use in a real computer, but this is a pretty decent way to think about how you do division. Essentially, division can be thought of as repeated subtraction, and that's what's going on here. So there's a little formalism up at the top. I tell it, yeah, the algorithm's name is division. I tell it what the inputs are. I tell the reader what the inputs are. They're a number and a divisor. And then there are local variables. I'm telling that up front. These are called Q and R for quotient and remainder. My first setup is I let the Q be 0 and the R is n. So set R at first to be the value of the number. And label 1 is something we'll come back to in a second. But, well, I might as well tell you. At the end of all this junk, see the statement that says go to 1? That's where we loop. From here, your bug goes, oh, I got to go to 1. And he jumps right back up to here and then begins running through junk again. All right, so when you have go to statements, you have to have label statements in there somewhere as well to say where to head to. All right, so inside this loop, if R is less than D, then we return. Now that is, I think that's interesting, right? That's the usual restriction on what the remainder should be. The remainder ought to be a number that's smaller than D. And by the way this R gets created and messed with, we're never going to have it turn negative or anything. So really the remainder is between 0, could be equal to 0, but from 0 up to, I guess, D minus 1. As soon as R is smaller than D, we'll know we're done, and then we'll return the quotient and remainder. Here's the real work, though. What we're going to do is add 1 to the quotient, and at the same time, or basically at the same time, we're going to subtract D away from R. This may look a little weird. Both of these assign to the variable what the variable used to be plus 1 here, and what the variable used to be minus D here. So that's actually slightly cheating. To do that requires an assembler to do a couple of other things. You can't just, well, there's no need to get into it. It seems reasonable to us that I've got R. I'm going to set R equal to itself minus D. And so what I'm doing here is subtracting D off over and over again. Each time I subtract a D, I bump up Q. And when I get the remainder small enough, if I've subtracted off enough D's, it'll be the right size to be truly a remainder, and Q will be the right size to be the quotient. You could think about this if you imagine having a handful of coins and you've got a bunch of friends around and you want to share them equally between your friends. So you sort of start passing coins out to each person. If there's D friends, or you plus them as D people, you lay out D coins each time you do that, and that's subtracting D from the ones that are in your hand. how many times you get through that is the number of coins each person gets. And that's really what division means, right? You're dividing a finite resource amongst d people. They each get n over d of them. Except ordinarily there's, it doesn't work out evenly. There's a few left over in your hand. And that's the remainder. Okay, so that's kind of a maybe over description of what's going on with the division algorithm. Let's look at how a trace table for the division algorithm would look as we run through it. We initialize the variables first. R gets set to the original. Okay, wait, I was using particular values as my n and d here. So n is 33, d is 7. Just a small example so we can see what happens. So we initialize, and the quotient is 0, the remainder is at 33, and then each one of these lines in the table is another pass through the loop. The first time q gets bumped up by 1 and r gets dropped by 7. 33 minus 7 is 26. Then q gets bumped up another time and 7 more off of the r. Keep going like that. At this point, at the last line here, the r we got is smaller than d, right? So actually, I think technically it's the next run through the loop where because that if statement happened right at the top of the loop. But anyway, the next thing that's going to happen is we'll return the two things. In this case, we'll return both the quotient and the remainder. Okay, so the other algorithm we want to discuss today is called the Euclidean algorithm. And to talk about that, you need to know about GCDs and LCMs. So let's briefly talk about them. GCD stands for greatest common divisor. And kind of like it says, it's the largest number that is a divisor of both of them. It's a reasonable thing to ask about, isn't it? I mean, so as an example, suppose we were asked to find the GCD of 105, excuse me, and 231. Now, let me do a little factoring work before we proceed. What are the prime factors of 105? Should I move that to the center so we can see it better? Well, I noticed that it's divisible by 5. You see that? So you pull off a 5, and what's left behind after pulling off a 5 is 21. Right? Oh, okay, so this is really easy. 21 divides into 3 and 7. So if we wrote out the prime factorization of this, typically you write them in increasing order, so we get 3 times 5 times 7. Yeah. Now, if I did the same thing for that other number, which I've forgotten, 231, whoops. All right, 231 tougher. Doesn't end in 5, so I know I don't have a 5 in there. Oh, here's a trick, though. Do you guys know about if you add the digits and you get a multiple of 3, then the thing's a multiple of 3? 231, that's 3 plus 2 plus 1, yeah, that's 6. So it will definitely have a factor of 3 in it. Let's get out the calculator for this. 231 divided by 3, 77. Ooh, that's nice. That's nice, because do you see the factorization of 77? That's easy, 7 and 11. All right, so the prime factorization here is 3 times 7 times 11. Now, keep those things in mind. I guess, I'll get it to the point where we can see both prime factorizations and then put this window back where it came from. And now, let's look at the next thing. Here's the divisors of 105. And here's the divisors of 231. And why did I want to find the factorization? Because that lets me figure out all the divisors really quick. First of all, 1 is a divisor of anything, so both of these lists have 1 in them. Both of them had a factor of 3, right? This one had a 3, and that one had a C. So in fact, all the primes that are the factors of the thing, they appear amongst the divisors, 3, 5, and 7 there, and 3, 7, and 11 below it. But the other things that appear are product of some but not all of the prime factors. So like this guy had 3, 5, and 7. 15 there is 3 times 5. 21, that's 3 times 7. And 35, that's 5 times 7. And finally, the number divides itself, so 105 belongs on this list too. And you can probably see the divisors of 231 work similarly, where you have 1, you have the prime factors, 3, 7, and 11, and then products of 2 primes. 21 is 3 times 7, 33 is 3 times 11, 77 is 7 times 11, and then the number itself, which is 3 times 7 times 11. Okay, so what's the GCD of these? You look at these two lists and find the biggest thing that's on both lists. And it's definitely not the 77. It's not on that list. Do you see it? 21. 21 is the GCD. This is actually even simpler if you just work with the prime factorization of the numbers. We had 105 is 3 times 5 times 7. 231 is 3 times 7 times 11. What primes do they have in common? 3 and 7. And so the product of 3 and 7, in other words, 21, will be one of the divisors of both of them. And in fact, since I've used sort of all the primes that they have in common, that's the biggest one that'll be a divisor of both. Cool. Yeah, the GCD is just the product of the primes that they have in common. That's a little unfair. If one of these primes occurred to a power, there could be powers on all the primes, and then it would be the largest power that both lists contained. So, well, that's for a later day. We'll work that out. The other thing we wanted to talk about in this section is LCM. That stands for least common multiple. And the way you compute it is similar. You make a list of multiples of the numbers. You have two numbers here, and you're going to list both of their multiples. Of course, unlike divisors, there's infinitely many different multiples of numbers. 1 times the number, 2 times the number, 3 times the number. There's bazillions. Right? There's a natural number's worth of multiples. But there are going to be some things in common between them, and we don't have to go forever because we're only looking for the smallest entry that's in both lists. Yeah, it's important to notice that there will be something in common between both lists, because if you just multiply the two numbers by each other, that if you've got A and B, well, the product AB is a multiple of B, but it's also a multiple of A. Yeah. Okay, so the product is on both lists, but there might be something smaller, and often there is. That smallest thing that's in common is the LCM, and that's the number that we use as a common denominator. When the numbers we're talking about are the bottoms of two fractions, the denominators of two fractions, the LCM is in fact the number you use as the common denominator. Here's an interesting rule, piece of algebra. I'm not going to try to prove this to you or even justify it to you, because later in your career in this course, you're going to be trying to prove that is true. It's not a hard thing to do, but I don't want to give it away right now. But the LCM is just take the product of the numbers and divide out by the GCD. That'll get you the LCM. Right? So look, if you know the GCD and you can multiply, then you can figure out the LCM, and you could work this around backwards, solve it for the GCD. And that means if you know either one of these, you can find the other one. So computer people would say they represent equivalent computational challenges. Right? You're just a notch away from finding one if you know the other. Okay, so let's talk about the Euclidean algorithm. Oh yeah, yes, that Euclid. This is an algorithm that is pretty old. It goes back to one of the later books of Euclid. You probably have heard of Euclid because of the books about geometry, but it's little known fact that he actually had way more than just the geometry books. There was books on elementary number theory, and even the beginnings of real analysis, and eventually three-dimensional geometry. So, but anyway, one of the latter books of Euclid contained this algorithm we're going to look at. If you had to factor numbers to find their GCD, like I just did, right? This work, that's fine when the number's in the hundreds or maybe even the thousands. But if you had to do factorization and find GCDs working with really big numbers, it would be bad because, well, this is why. There's a lot of applied number theory going on in the world right now. There are several. The most famous one is called RSA, but there are several public key crypto systems that are used to allow for secure communication over the internet. So, in particular, when you type in your credit card number on an Amazon.com site, they're using public key cryptography to keep that hidden from anybody who may be listening in on that communication. And that public key crypto stuff requires us to take the GCD of numbers, often numbers that have many hundreds of digits, at least 100. That's the least secure system anybody uses now, but often 500 or 600 digits can be used. Basically, this public key crypto stuff works on the fact that on a computer, at least, it's not that hard to multiply two numbers together that have a couple of hundred digits. It takes actually a fraction of a second. But if you just tell me what the product is and ask me to figure out that factorization, I could be here for centuries. So that's known as a trapdoor function. And anyway, all the crypto systems rely on some kind of trapdoor system. And in order to use the most famous one, RSA, you need to be able to take the GCD of pairs of numbers of this enormous size, many hundred digit numbers. So if you had to factor, you'd be lost. You couldn't do it. Well, unfortunately, I say, it's in a book by Euclid. Nobody actually knows whether Euclid wrote those books. He might have just been collecting a bunch of stuff by other people. There's even some people who think such a person didn't exist, that Euclid was like a pen name for a whole group of people. But anyway, somebody back in ancient Greece already found a method. All right, so we can apply the Euclidean algorithm even with numbers that have hundreds of digits. Clearly the Greeks weren't thinking about that, but hundreds of digit numbers, you can run the Euclidean algorithm and it runs quickly and you'll find their GCD. And the algorithm has a key thing that really makes it work. So I'm calling the numbers A and B that we're looking to take the GCD or find the GCD of. And usually we take A to be the bigger one. If not, then switch them around. call A the bigger one. You can use the division algorithm to write A as a quotient times B plus a remainder. Right? And here's the weird fact that just almost remarkably happens to be true. The GCD of the first two numbers we started with, A and B, is exactly the same as the GCD of B and whatever remainder you got. Well, that's just trading one problem for another, and they're both GCD problems. But notice that A was the bigger number, and we've dropped it. So B is the smaller number, and R is smaller than B by definition because it came out as a remainder. The divisor here was B. So B and R are a smaller pair of numbers than A and B were. That's awesome because you're now doing an easier version of the same problem. So you repeat it. So here's the algorithm. Like I did before, I put some stuff up front to just give a name for the algorithm and talk about what its inputs are and what variables we use on the inside of the algorithm, so-called local variables. It's Q and R. Like before, I have a main loop, a single main loop. And so there's a go-to one at the end and there's a label one at the beginning. Those things mark off the statements that'll be run over and over again. So first, we just calculate Q and R from the division algorithm with A and B as its inputs. That's what the algorithm we previously defined did. It took A and B and produced the quotient and remainder. And here's our stopping criterion. This is where we'll jump out of the loop and actually exit the program. And if R happens to be 0, you're done. Now, how do we know that R will eventually hit 0? That's a good question. We'll see that it will, but it's something to be worried about because if R never does get equal to 0, this is going to just loop forever, which would be bad news. Take up all your computer cycles. But if R is 0, we'll return. So before R has gotten set to 0, we replace A with B. Right? We're setting A equal to B, and we replace B with R. That's what that little statement on the previous slide said. Can I go back? The GCD of A and B is the same thing as the GCD of B and R. So I just want to make A be B and B be R, and run it again. So we go through the loop a second time, and then we'll have new values for A and B, the new values of Q and R and new values for A and B. So let's see how this runs with an example. I picked an example that's fairly big so that, it would seem like we were doing something real, but it turns out the algorithm completes in just 5 steps through the loop there. So the numbers were 341 and 248. Okay. So first I just initialize the variables. That's what the first line is. A is 341, B is 248. And I just set Q and R to 0 at first because I don't know what they're going to be. The first pass through the loop, A hasn't changed, A and B haven't changed, but I've done the computation. I found that the 248 goes into 341 once, and the remainder is 93. Do we believe that? You can certainly verify it on a calculator. 341 divided by 248 is 1.375. The 1 in there, that tells you what the quotient is, 1. And the 0.375 tells you what the remainder is. But do it this way. Subtract away the 1, so you just get the decimal part of that number. And then times it by the thing you were dividing by. We were dividing by, was it 248? So, whoops, I said times. I want to times by 248. Because that 0.375 on the end is really 93 over 248. It's the remainder over the divisor. Yeah, so there you go. Quotient is 1, remainder is 93. Now, notice how things move around as we go to the next iteration. At the end of the loop, we set A equal to B and B equal to R, and that's what's happening in this next line. The value of A has become 248, what B used to be, and the value of B is 93, and that's what R used to be. And there we're going to calculate with that A and B. Turns out the quotient is 2 and the remainder is 62. Let me do it anyway. That's 248 divided by 93. 2 and 6 is repeating forever. So the quotient is 2, that part we're seeing. Apparently the 0.666 is really 62 over 93. Is 62 divided by 93 really? Oh yeah, it is. Okay. So Q is 2, R is 62, and those move into the A and B variables. Well, the Q doesn't. Actually, it's kind of interesting to note, we just throw away the Q. We don't even need that. But we do keep track of the R. R moves where B was, and B moves where A was. All right, so now we're looking at 93 and 62. I can probably see that by I, that it goes in once and the remainder will be 31. Okay, so the next iteration through the loop, A is replaced with the 62 that came from B, and B is the 31 that came from R, and that goes in twice and there's no remainder. Beautiful, because that's the signal that we should return. Oh, I probably should have said return what? What is the answer? Well, it's 31. It's the last remainder you got before you went, and it's also the last value that's in the register that's named B. Let me back up the slide one. You notice how it said it in here. When R was 0, what do? We return B. Okay. So that's the end of the slides here. And I guess that's the end of the section on algorithms. We'll be back in 24 hours with lecture 6. Have a great rest of your day.